All right. Now, one other thing that I want you guys to do, take out your Chromebook and have Desmos open, ready to go. So have Desmos open, ready to go. Once you get it open, clamshell your Chromebook. So have it open, so when I tell you to have it up, it's ready to go. But once you do have it open, just clamshell your Chromebook. So have Desmos open, and then clamshell your Chromebook. Over here. All right, does everyone have Desmos up? So once you got Desmos up, just clamshell your Chromebook. We'll come back to it in a minute. I just wanted you to have it up so it's ready to go when we get to it. So you should not be on anything else besides Desmos. Once you have it up, clamshell your Chromebook. You should not see your Chromebook all the way open if you have Desmos out. All right. Shh. So, when graphing cube root or square root functions, every cube root or square root function is going to span from one of these two. So, square root of x, that's obviously the square root function. Cube root of x, that's the cube root function. Now, these two specific, all square root and cube root functions stem from them. What is that called? That makes those functions the what type of function? We talked about this with quadratics. Owen.
Parent function.
Right. It makes these both the parent functions. Meaning, these are the mother of all square root and cube root functions. So square root of x is the mother of all square root functions. Cube root of x is the mother of all cube root functions. Every other square root or cube root function is just a transformation of these two. So knowing what they look like is important. So let's start with square roots. So we're going to start by making a table. Now, I want you guys to think logically about this. Obviously, for x, what are we going to want to put as values for x? What would make the most sense to put as values for x? That'll make it very, very, very easy to graph. Not whole numbers. So think about it. Whatever number we put in for x, we're then going to square root it to get our y. So what numbers would make the most sense to put in for x? Be what? Nope. 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 Guys, we've been dealing with them a lot when we were simplifying. No. What? Close, but no. Perfect squares. Thank you. You want to put in perfect squares in for x. So our x, we want it to be perfect squares. Meaning when we take the square root, we get a nice whole number, not an irrational number. So think logically about this. What is the lowest most number that's a perfect square that I can put in for x, that when I take that square root, it still gives me a real number, not imaginary? Nope. 0. So 0 is the lowest number I can put in. And what's the square root of 0? 0. If I go any lower than 0, so let's say I put in -1 in for x, what happens? They're imaginary, which we can't graph imaginary. All right, so we want to graph all of its real numbers. So we want real numbers, real rational numbers, I should say, for y. So what's the next perfect square that I can do for x? What's the next perfect square I can do after 0? The next one up. 1. Square root of 1? 1. What's the next perfect square I can do? Nope. 4. 2 is not a perfect square. 4 is. However, the square root of 4 is 2. And then what's the last one that'll fit on this graph? 9. Square root of 9? So if I graph this, I have 0, 0, 1, 1, 4, 2, and 9, 3. So the graph looks something like this. Now, look at the shape of the graph. What does it kind of look like to you? Kind of. But what does it remind you of? Maybe it's oriented differently and maybe there's some pieces missing. Would it make a bit more sense if I do this? Now you don't have to draw that line, but what does that look like? Anyone? Starts with a P.
Kind of like a parabola.
A parabola, but sideways. Why is that true? Parabolas we mostly associate with what type of function? Come on, we had a whole unit on it. We had 2 whole units on it, actually. Parabolas are associated with what type of function? Starts with a Q. Quadratic. Which means x squared. Well, what's the relationship between x squared and square root of x? They cancel each other out, meaning they're inverses of each other. All right, so that's just something to keep in mind. So, the pattern of the square root function, pattern I would really say is this table you just got to know. You got to know that table. So in other words, x values are perfect squares. Y values, you want to be real rational numbers. Now, the domain. If I look at this graph, what is the domain of this function? So domain means what? What type of values? X values. All right. So what's my lowest X value? So we're going from left to right. 0. Now, will we put a bracket or a parenthesis with that? Is it defined at 0? It's a bracket because it's defined at 0. What's the highest X value? So the rightmost X value. Infinity. It goes on forever. Granted, very slowly, but it'll still go on forever. So the domain is from 0 to infinity. You can also write that as x is greater than or equal to 0. So as long as you understand either the interval notation or the inequality notation, it's fine. What about the range? Range is y value. So what's my lowest y value? 0. Bracket or parenthesis? Is it defined at 0? Yes, so we use a bracket. What's the highest y value? Infinity. It does go up forever, just very, very slowly. And we can also write this as y is greater than or equal to 0. So I don't care which way you write these two, they're pretty much the exact same thing. Whichever one you understand the most. So that's the parent function of a square root. Now let's look at the parent function of a cube root. So still going to do a table. Now, we were looking for perfect squares for the x values of the square root function. So what do you think I'm going to be looking for the x values of a cube root function? Perfect cubes. Now, what is true about cube roots that's not true about square roots? So in square roots, we couldn't have negative numbers as x values, but can we have negative numbers in cube roots? Yes. If you take the cube root of a negative, you still get a real number. It's just a negative number. So I'm going to start us off. I'm going to do negative 8 first. What's the cube root of negative 8? Negative 2. All right. So our y values are still real, rational numbers. What's the next perfect cube down from negative 8? Negative 1. What's the cube root of negative 1? Negative 1. What's the next perfect cube down from negative 1? 0. Cube root of 0. 0. What's the next one?
1.
1. Cube root of 1. Positive 1. What's the last one? 8. Cube root of 8. 2. So in reality, that table's pretty easy. You just start with negative 8, and then it essentially just repeats itself, but you change the negatives to positives. So if I graph this, I have negative 8, negative 2, negative 1, 0, 0, 1, 1, 8, 2. So the graph looks something like this. Now, the pattern, once again, you've just got to know this table. Trust me, this table will help you when you're graphing other types of cube root functions. Knowing the parent function table is important. And again, x values, we're looking for perfect cubes. Y values, we want to make sure they're real, rational numbers. And remember, rationals can include fractions. So if you get like a terminating decimal, that's okay, like a 0.5 or something, that's fine. We just don't want weird ones that we have to round. So, what's the domain of this function? Negative infinity to positive infinity. So what's the other way to state that? So if we're going from negative infinity to positive infinity, what's the other way to state it? All real numbers. So you can either write the interval notation or you can draw the R with a line through it. What's the range? Negative infinity to positive infinity. Make sure you go from smallest to largest. So it's all real numbers again. Because again, there's no restrictions on cube roots. Cube roots will never create imaginary numbers. Only square roots do. Now, if we want to talk about the rate of change for the square root. So rate of change just means how fast it's growing. Compared to other functions that we've seen, what's true about the rate of change of this function? Is it going up faster or slower than functions that we're used to? It's definitely slower. In other words, it's getting bigger slower. So what's true about the rate of change? It's slower than other functions. So quadratics get big really quick. Exponential get big really quick. Even linear gets big pretty quick depending on what the slope is. But a square root function, they get big really, really slow. Meaning, when we're at x is equal to 100, what's the y value? When x is equal to 100 of the square root function, what's the y value? 10. So we can be all the way at x equals 100, and we're only up to 10 on the y values. So it gets big very, very slow. Now, that's the parent function, so that's something you got to know. Now, the next little bit talks about the different function transformations. So knowing these will help you graph your square root, cube root functions. All right. So first things first, the general form here. So the first one says f of x plus c. So the c is on the outside of the f of x. What's another name for f of x? Y. Good. So in other words, we're doing y plus c. That's another way that you can think about it. So I want you guys to think about this logically. We're adding something to the y value of the point. So what's going to happen to your graph if we add something to the y value? It's going to go up. And that's exactly what it does. It shifts up. However many units. Shift up c. So whatever your c value is, that's how many units are going up. So for example, if it's not under the radical, it's considered affecting the y value. Okay, so we're adding 5 to this one. So what are we actually going to do? We're going to
subtract 5.
Function transformation. So it's the parent function plus 5. So what's the graph going to look like? It's going to shift up what? 5 units. Good. Now on the opposite side, when we have a minus c, so we're looking at y minus c, y is vertical. We're subtracting to the y value. So what's happening to the point? It's shifting down. However many units c is. So we have the parent function of a cube root, but we're subtracting 8. So am I going up or down? Down. So I'm going down what? 8 units. I should say shift. Now, these next two are a little bit weird, but if it's under the radical or inside, it's affecting x. All right. Now, plus c is actually shift left c. It's the opposite of what you normally think. It's kind of similar to, do you guys remember when we did vertex form of a quadratic? So like it was this. And then when we pulled out the vertex, we always had to flip this sign. You guys remember that? Kind of, sort of. It's the same thing. So if we have a plus 2 under the radical, that means we're going to shift left 2 units. On the flip side, if you have minus, again, it's still affecting the x. So both of these are affecting the x values. You're going to shift right c. So these two are opposite what we would think logically. So it's opposite logic. So whatever you think it would be logically, it's the opposite. Because obviously if we're subtracting from the x value, you think you'd be going to the left. If you're adding, you think you'd be going to the right, but it's the opposite. And there's mathematical proofs that show the reason why, but it'll go right over your head. So just trust me when I say it's the opposite. So this one, it'll be shift right 9. Now this last one, they're making your y values negative. So if the y values become negative, but the x's remain the same, what actually happens? It does what? Say it one more time. Doesn't change them both negative. The x's will remain the same, but the y's will flip. So think back, way back to unit 1. What type of transformation is that? It's a reflection. Over what axis? Nope. It's actually the x. The x's stay the same, but the y values change. So it's a reflection over x-axis. So if you see a negative on the outside of that radical, you're going to reflect over the x-axis. Which all that means is just make your y's negative or flip the sign of your y's. So let's try a couple of these. So let's look at example 1. So if we started with the parent function, square root of x, and then we went to this function, square root of x minus 3, what happened? From this function to this function, what do? We shift down what? Down 3. Good. So if we started with this, the parent function of the cube root, and we went to this function, which is negative cube root of x minus 2, what do we do to go from here to here? We reflect over x. Not down 2. Nope. Right 2. It's under the radical, meaning it's affecting the x's, so you have to go right 2. You got to look at the placement, guys. If it's outside the radical, you're going up, down. If it's inside the radical, you're going left, right. All right, last one. So we start with the parent function of the square root, and we go to the square root of x plus 7 under the radical plus 9 outside the radical. So how do I go from here to here? Not up 7. Nope. Left 7. And then up 9. So guys, knowing these rules right here is important. All you got to do is just look at the rules. So, that being said, let's try these two. Now, the easiest way that I tell students to do this is to look at what your x's and y's are affecting. All right. So, just make a note. If it's an operation outside the radical, it affects y, meaning you do that operation to the y value. But if it's under the radical or inside the radical, it affects x. So you do that to the x value. So what I tell my students is always start by having your original table or your parent function table. So for a square root function, what's my x values of my parent function? So it's on the previous page. What is on my table for my parent function of a square root?
0, 0.
0, 0 is the first point. Then
1,
1, 1. Someone besides Owen next. 4, 2. Then 9, 3. You always are going to start with this table. So this is your parent table. Now, we're going to figure out what we need to do to our x's and what we need to do to our y's. All right. So let's look at x's first. So remember, x is going to be under the radical. So that's what's affecting our x's. Now, it says minus 1, x minus 1. We're actually not going to be subtracting 1 to x. We're actually going to be doing the opposite. So adding 1. Why does that make sense? What's the lowest value when we evaluate that we can have under the radical? 0. Well, if we subtract 1 from 0, that gives us negative 1. Is negative 1 minus 1 0? Is negative 1 minus 1 0? No. Negative 1 minus 1 is negative 2. But what number subtracted from 1 is 0? Positive 1. 1 minus 1 is 0. All right. So what we're actually going to be doing to our x values here is we're going to be adding 1. So in other words, you're going to do the opposite of what's under that radical. So, and it makes sense because what direction are we going here? What's the direction? No. X values, left, right. Look at the table, guys. You're going right 1. So obviously, we're going to have to add 1 to make it go right 1. So I'm doing x plus 1 to get my new x value. So what's 0 plus 1? 1. 1 plus 1?
2,
4 plus 1?
5,
9 plus 1.
10.
So we're taking these values and we're adding 1 to them. So we took these, added 1 to them, and that'll take care of the right one. Which makes sense, because isn't 1 to the right of 0? So isn't 1, which is right here, to the right of 0? Yes.
Yeah, it is.
Now, next thing that we got to do is our y's. So what's affecting our y's is here and here. So what's the operation that, now with the y's, we don't have to do the opposites. We just do what's there. So what operation are we doing here? No. What's this number doing to this radical? It's multiplying. So we're doing multiplication and then addition. So, in other words, we're going to multiply the y value times 2 or times -2 and then add 5 to it. So, let's just talk our way through it. What's 0 times -2? 0 and then plus 5. 5. So 1, 5. So we're taking these and we're affecting the y value at the same time. All right. What's 1 times -2? -2 plus 5. 3. What's 2 times -2?
-4.
Plus 5.
1.
Good. And then finally, what's 3 times -2?
-6.
-6. And then plus 1.
-7.
No. Plus 5. -6 plus 5. -1. And just like that, this is the table that we're going to graph. So my new points are 1, 1, 1, 5, 2, 3, 5, 1, and 10, -1. So my graph looks like this. Now, let's say that this was on the test and you completely forgot how to do this. Where do you go? Desmos. So let's do that exact same thing, but in Desmos. So I'm going to type in the function first. So I have -2 square root of x minus 1 and then plus 5. Make sure the plus 5 is outside the radical. Now, couple of things when you graph. You always want to fit your axes and you only want the rational numbers. You don't want weird decimals. So, what would be the most logical thing to do when you're trying to get points that work for this graph? Because I don't want just, you just draw what it looks like on the graph. I don't want to sketch. I want exact points. You will not get full credit if you do not put exact points. So how do I get exact points? Guys, I know I've taught you this. How do you get exact points in Desmos? You generate a table. How do I generate a table? You click the gear key, and then I click what? Table. Now, if you look, all right, with all of these, they say undefined. That's because that's when you get into imaginary territory. But then it starts at 1 and 5. All right. So you get 2, 3. My recommendation, just keep adding in numbers. So if I put in 3, notice I don't get a nice decimal. All right, so that's not going to be a number I graph. All right, let's try 4. Also not a nice decimal. Not going to be a number I graph. 5, nice number. Okay, so how do you know what numbers to put in for x? Look at what's under your radical. You want to shoot for x values that when you subtract 1 to them, give you a perfect square. So 1 minus 1, that's 0. That's a perfect square. 2 minus 1, that's 1. That's a perfect square. 5 minus 1, that's 4. Perfect square. So it will be the other x value I want.
Um, 9.
Well, 9's what you're shooting for is the perfect square, but what number minus 1 would give you 9? Minus 1. 10. Perfect square. Now, if you forget that, that's fine. Just keep typing in numbers until you get a couple of ones that don't have weird decimals at the end. So again, do not graph these weird decimals. Keep typing in until you get, just like go down the line and keep typing in until you get some nice numbers that fit on your axes. So if your graph, your x values only go to 10, you don't need to go past 10. I only want what fits on the graph. All right. So that being said, use the Desmos method and try that next example to graph on your own. So use the Desmos method to graph the next one on your own. And I want nice y values. So when you get your table in Desmos, I want you to write the table that you actually graphed on your paper. So I want to see your T-chart of the points that you actually use from Desmos. But make sure you only want pretty numbers as your y values. So keep typing in until you get some pretty numbers. Now, if it's a decimal, that's fine. So like if you get like 0.5 or something, that's fine. I just don't want like 0.3578492 whatever. Continue. But if the decimal terminates, that's fine. Just however many you can fit on the axes. So keep going until like you shouldn't be able to go past 10 as your x value because it won't fit on your axis. So again, you want nice rational numbers. If the decimal terminates, it's technically a nice rational number. Make sure you write a table of the points that you actually graphed on your paper. So you don't have to include the weird points that Desmos gives you, but I want the points that you actually graphed. Okay, you guys, about 1 more minute. I don't have it. I already gave it out.
Yeah. Okay.
All right, let's move on. So Someone raise their hand and give me 1 point that they graphed. So it's 1 point that you definitely graphed on your graph. Rajan. Okay, 4, -7. Okay. What's another point that you definitely graphed on your graph? 0, -8. What else? 1, -7.5. There's one more. Owen.
9, -6.5.
Right. So that's all the x values that you can fit on your graph that are defined. So we're going to leave it with that. So I have 0, -8. 1, -7.5. So you just kind of go halfway between -7, -8. 4, -7. 9, -6.5. So it looks like this. So again, if you were in Desmos, all right, I already generated the table. -7.5 is a rational number because that decimal ends. -7.2928932, and it's going to keep on going forever and ever. That's not rational. It's irrational. So all you got to do is just keep typing in until you got some nice numbers. So there's another one. That one doesn't work. That one doesn't work. That one doesn't work. That one doesn't work. That one works. And then try 10 because that's all you can fit on the graph. That one doesn't work. So that's how you know, guys. And as you put it in, write down on your paper the ones that do work so that you can plot them. Does that make sense? How that works? Yes, no, maybe. Okay. Now, next thing we're going to do for these two is state what the domain and range are. So for this first one, the purple one, what will be the domain? So what's the lowest x value? Not 0. Nope. What's the lowest x value? Left to right, what's the lowest x value? No. Guys, if I run my pencil from left to right, all right, so if I'm running from left to right, what's my lowest x value? 1. All right, what's my highest x value? So my rightmost x value? Nope. Arrow, infinity. Other way you could write it is x has to be greater than or equal to 1. Range. What's my lowest y value? So what's my lowest most y value? Negative what? Negative. Nope. Arrow. Negative infinity. What's the highest? Five. So that would be y has to be less than or equal to 5. All right, come over here. What's my lowest or leftmost x value? Nope, that's y. X. X. 0. What's the highest? So the rightmost y value. I mean, not y, x value. Arrow. Infinity. Good God, guys. You've been doing this since Math 1. Oof. So x has to be greater than or equal to 0. Lowest y value. Low.
At
Negative 8. Good. Highest. Oops. What's the highest? Highest.
infinity.
Infinity. Guys, you gotta know how to do this. It's gonna haunt you in math 3 too. So you gotta start at the leftmost for domain, go to the rightmost. If you see an arrow, it goes to infinity. All right. Same thing with range. Start at the bottommost, go to the topmost. You gotta know how to do this. All right. Now, we're going to do the same thing pretty much for these cube roots. Now, we'll do the first one together. So, just so you're aware, what's my cube root parent graph? What's the table for your cube root parent? Guys, it's on your paper. What's the parent table for a cube root function? -8, -2, -1, -1. Then, good. So you got to be keeping that in mind as you're doing a cube roots. Meaning, you need to start with some negative numbers or some very small numbers. All right. So I'm going to graph this in Desmos. Now you need to watch me because you can't just click this key and do a cube root. It doesn't work like that. So to graph a cube root in Desmos, you got to hit functions and scroll down. You're going to scroll all the way down to the very bottom where it says number theory. Do you guys see right here where you see in and then a square root symbol or a radical? Click that, and then it'll let you input the 3. If you don't put the 3, it won't graph it right. And then x minus 5. Now, I'm going to generate this table. So, as of right now, I just got a bunch of irrational numbers. That ain't going to float. So, my suggestion is, since a cube root can span the entirety of your x-axis, start with -10 and go down the line. All right? So that's what I'm going to type in. So I'm going to have -10. Doesn't work. Try -9. Doesn't work. -8. Doesn't work. -7. Doesn't work. -6. Doesn't work. -5 doesn't work. -4 doesn't work. -3. Oh, we got a winner. So that'll be my first point. So go back to your graph. You have -3, and then its y value, which was what? -2. All right. Now, we don't have to type in -2 through 2 because it's already at the top. None of them worked. So we're going to pick up with 3. 3 doesn't work. All right. 4. Oh, got another winner. So I have 4. What was it? -1. Okay, keep going. 5. Oh, got another winner. 5, 0. Keep going. 6. Oh, got another one. 6, 1. 7 doesn't work. 8 doesn't work. 9 doesn't work. 10 doesn't work, and we've officially run out of graph. All right, so that's what you need to do when you're graphing this. Okay, look at the axes, specifically the x-axis. So look at the x-axis and see the numbers that you have to go through and just test them. Okay, you can do that for both square root and cube root. Test all the numbers, write down the ones that work. All right, you just want the numbers that can fit on your graph. If they don't fit on your graph, what's the point of finding them? So this is what I'm going to graph. I have -3, -2, 4, -1, 5, 0, and then 6, 1. So it'll look something like this. All right. What's the domain of this function? What's the domain?
-3.
Nope. Negative infinity to positive infinity. Both ends have arrows. They go on forever. You can also say it's all real numbers. What about the range? Come on, guys. Negative infinity to positive infinity. Good. Even though it's going up and down very slowly, it's still going up and down completely. So it's all real numbers. I'll give you a hint. This is true for all cubic functions. They're always going to be all real numbers for both, or cube root functions. All right. Now, before I get you guys to graph the next one on your own, this one's a little bit different. It has a fractional exponent of 1/3, but that's the same thing as a what? What type of functions are we graphing? Cube what? Roots. So this is the same thing as negative cube root of x plus 3. So what I want you to do is graph that in Desmos. Don't forget the negative. All right. Pay attention to your x-axis. That's all the x values you need to be testing. Write down your table and then graph it. So that's what you guys should be doing. And I want to see the table. This will be true on your test. If I don't see the table, I'm not giving you credit. So go through from -10 to 10. Check all those numbers. I only want the ones that give you nice, pretty numbers. If they give you funky decimals, you don't even need to bother. Mm-hmm. Mm-hmm. So guys, once you get a good enough table and you've checked all the numbers from -10 to 10, graph it. All right, thumbs up if you're ready. All right, guys, for time's sake, I gotta move on. So that's the table I came up with. That's the graph. That's the domain and range. How'd you guys do? Did you guys do okay? It shouldn't be too hard. Desmos is doing all the legwork for you. All right. Now, stepping away from graphing and going to actually writing the equations. So, when it comes to writing the equations, first you got to identify whether it's a square root or a cube root. Is this first one a square root or a cube root? It's a square root. So it's going to be something, y equals something, square root. Now, my recommendation, take a minute, graph the parent function of the square root. So that'll be 0, 0, 1, 1, 4, 2, 9, 8. So 0, 0, 1, 1, 4, 2, 9, 3. I don't know why I put 8. So it looks like this. Now, you then want to look at it from here. So I'm just plotting some pretty points. So how did I get from the purple to the black? So I would look specifically at these points right here. How did I get from here to here? What did I do? I went to the left, not 8. Left 6. So we went left 6, and that's all we did. How do I translate that to a function? So look back at your function transformations. If I go left 6, how would I write that? Not x minus 6, x plus 6. And is it going to be outside the radical or under the radical? Under the radical. So that's the equation. So that's all you got to do, guys. Just take a minute, draw the parent function, and just look at where it goes from. Okay. The cubic function. Again, I'm just going to draw the parent function of the cubic. So -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. And the more you do this, the more you'll remember it. Now, if I put some happy points here, let's see, here, 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 then here. So, again, biggest place to look is probably this middle point where it does the little squiggle. How do I get from here to here? What do I do? I went up and right. So how many did I go up? I went up, not 5. Yeah, no, I went up 5. I went up 5. Yeah. I went up 5 and then right how many? 2. So I'm going to translate that to my function. The cube roots of, so under the radical is the right. So how do I write it? X what? How do I write right 2? Nope. Minus 2. And then up 5. Plus 5 outside the radical. So up 5's here, right 2's here. And that's your function. So whenever it asks you to write the function from a graph, just take the 2 seconds to draw the parent graph and always go from parent to the new. And just pick a point. All right, last thing we got to talk about. How to calculate the domain without looking at the graph. Now, obviously on your test, you will have full access to Desmos. So if you can't get the domain from looking at the Desmos graph, then what the heck? But here's the other way you can figure it out. We already know that we cannot take the negative of a square root. Specifically, we don't want imaginary numbers, which is what happens when you take a negative of a square root. That means x minus 4 has to be greater than or equal to 0. Because 0 is our lowest real number that'll give us a perfect square. So we can solve that to get the domain. So in other words, you take what's under the radical, set it as greater than or equal to 0. So x minus 4 greater than or equal to 0. How do I solve for x?
Add 4 to both sides.
Add 4 to both sides. X is greater than or equal to 4. Guess what? You just got your domain. Which you can also write that as from 4 to infinity. So whatever's under the radical, you set that greater than or equal to 0 and then solve for 0. Solve for x, sorry. So for this one, 2x plus 5. I'm going to set that greater than or equal to 0. What do I do? Minus the 5. I get 2x greater than or equal to negative 5. Divide by 2. X is greater than or equal to negative 5 halves. There's my domain. Now, to get the range, all you got to do to get the range is plug the number back in for x. Or put that number into the Desmos table. And it'll generate the y value. So, let's try a couple of these. All right, so if I have x greater than or equal to 0, that's my domain. I just took that, did that. So in interval notation, that means it's from 0 to infinity. If I plug 0 back in for x and evaluate that, so I have 5 square root 0. What's that equal to? 0. So that's my y value. And we're not reflecting, so it still remains as y is greater than or equal to 0. So 0 to infinity. Now, if I look here, all right, I do x minus 7 equal to 0. Greater than or equal to 0. So x has to be greater than or equal to 7. So it's from 7 to infinity. Now, if I plug the 7 back in, I have a negative, so mind the negative. That means it flips. So we'll still get 0, or y is 0. But because it flips, that means instead of greater than or equal to, it's less than or equal to 0. So it's from negative infinity to 0. So again, if you have a negative, the range flips. Not the domain, the range. The domain typically remains as greater than or equal to. But the range can flip depending on if it's negative or not. Cubic functions, just know for a cubic, it's always going to be all real numbers. So if you see that cubic, it's all real numbers. Any questions? All right, so that's it for today. Now, the delta math is assigned to you guys. It is 5.6 through 5.8. We only got through 5.6 today, so you should only be able to do like the first 4 sections or so. So just anything that says graphing and radical, you can do that. Radical graphing or roots graphing, you should be able to do those. Make sure you clean off your whiteboards before you leave, put your calculators up, all that good stuff.